Okay, so I want to illustrate this with an example. So I'm going to revisit one of the first groups that we studied, S3 revisited. So S3, remember, is the symmetric group. The the terminology I want to use is symmetric group on 3 letters. In other words, it is the group of bijections from a 3-element set to itself. Okay, in my earlier notation, which was given in my first video, I concretely told you what the 6 bijections are and gave them the names F1, F2, F3, F4, F5, F6. Now I want to give a more logical, more clear notation for this group, because obviously this is not useful. Right now, what is F2? You have to go back and see what I have called F2. So instead of doing that, I am going to give you a different description of S3, and in subsequent lectures I want to use that description. So I want to introduce a new notation to describe elements I want to use a notation which is useful to understand what that element is doing, because here I have no idea what F2 does, no idea what F3 does. So my notation, I want to immediately looking at the notation, I need to know what element, what it does as a function, and I also don't want unnecessary information. So let me introduce this. This is called the cycle notation. So if you recall what F2 was, so I will just do it for one element or 2 elements. F2 was the function which sends 1 to 2, 2 to 1 and 3 to 3, right? So this was the function. So let's look at this carefully and how to minimize the data that I have written. All these things, a lot of it is unnecessary. For example, 3 goes to 3, that means that I know I would like not to mention that at all in my description. So in the new notation, let me write this as simply 1, 2. So all my elements of S3 will be denoted by elements 1, 2, 3 within brackets. Okay, so and I will tell you how to read this. First of all, any number that does not appear here is supposed to go to itself. So 3 is not appearing here. So this is supposed to stand for F2. 3 is not appearing here, so that means 3 goes to 3. And where does 1 go? It goes to the next number there. It goes to 2. Where does 2 go? It doesn't have anything to the right, so you cycle back to the beginning of the expression. So 2 goes to 1. So 1, 2 sends 1 to 2, 2 to 1 and 3 to 3. So you can definitely agree with me that this is a much simpler notation than writing all this data here. And the advantage, of course, is also that just by looking at it, you know what it does as a function. It sends 1 to 2, 2 to 1 and 3 to 3. So you can replace F2 with 1, 2. So in the same way, if you replace, use this notation, what does F3 do? F3 sends 1 to 3, 3 to 1, 2 to 2. So in this notation, in the new notation I am introducing, I start with 1. Okay, where does 1 go under this? It goes to 3. So I put 3 next to 1. And where does 3 go? It goes to 1. So I don't want to write a number again. So I'll remove 1 and I start the bracket. I put 1. 1 goes to 3. So I put 3 there. But 3 goes to 1. So I close the bracket, because then once you look at the last number on the bracket, before the bracket, it goes to the first element in the thing. In other words, it goes to 3. So remember, in this new notation, if I use 3, 1, it will be the same element, because 3 goes to 1 and 1 goes to 3. And I am not going to introduce, I'm not going to write anything about 2 in this notation, because 2 is supposed to go to itself. In the previous term also, 1 2 is also can be written as 2 1. The point is 2 goes to 1, 1 goes to 2. So it will take some time for you to get used to this, but this is a very useful notation to represent bijections of sets. 1 goes to 3, 3 goes to 1, 3 goes to 1, 1 goes to 3. That's the same function. What does 1 F4 do? It fixes 1 and it sends 2 to 3, 3 to 2. And again it's clear, 1 goes to 1, so I don't want to even write 1 in the new notation. So I start with 2, it goes to 3, 3 goes to 2, so I close the bracket. F5, F5 was 1 goes to 2, 2 goes to 3, 3 goes to 1. So this is more interesting. So now let's put the bracket and start writing the cycle notation. I put 1, 1 goes to 2, so I put 2, 2 goes to 3. Now I cannot close the bracket like earlier, because 2 doesn't go to 1, 2 goes to 3, so I have to put, and 3 has not appeared so far, so 3 must be put next to 2. But now 3 goes to 1, so 1 is the first element, so I close the bracket. But again, just like before, I can cycle them and I don't change the function. So for example, I can do this, also write this as 2 3 1, 2 goes to 3, 3 goes to 1, 1 goes to 2. I can also write this as 3 1 2. So there is some ambiguity in which order what you start with, but there is no ambiguity in the order in which they appear. So the correct way to think of them is 1 2 3. So this is 1 2 3. If you go clockwise, 1 2 3. It doesn't matter where you start. If you start at 1, you have this description. If you start with 2, you have this description. But 2 3 1, it's important to traverse these things in the correct order. If you go clockwise, 2 3 1, or you can start at 3 3 1 2. So that's this cycle. Here it is 2 and 3, and you traverse in clockwise order. So 2 3 or 3 2. Finally, what is F6? F6 was 1 goes to 3, 3 goes to 2, and 2 goes to 1. So if you write the cycle notation, you put 1, then you put 3, because 1 goes to 3, 3 goes to 2, and 2 goes to 1 again, so you close them. So in the cycle notation, you have 1, then 3 and 2. So 1 3 2 is same as, you can start with 3 3 2 1 or 2 1 3. Remember that in no convention these two elements will be same, because 1 goes to 2 whereas 1 goes to 3 here. Only thing you have to keep in mind is, in a cycle notation, these are called cycles, the image of an element is determined by what comes after it. In this notation, image of 1 will be 3, image of 3 will be 2, and if the element is at the end of the cycle and the next element next you see the bracket closed, its image is the first element of the cycle. So 2 goes to 1, 1 goes to 3, 3 goes to 2. So in this notation now, S3 is identity element. I will now as always denote by E. You have 1 2, 1 3, 2 3, 1 2 3 and 1 3 2, right? And you agree with me hopefully that it is much easier than before. Earlier I was calling them F1, F2, F3, F4, F5, F6, and if you just tell you what is F2, you have no way of remembering it, right? You have to go and see where we have defined F2 and see what it is. Now it doesn't matter, I can forget that earlier notation. If I consider for example the function 2 3, it's clear that it sends 2 to 3, 3 to 2 and 1 to 1. 1 to 3 sends 1 to 2, 2 to 3, 3 to 1 and so on. So let's, I have given this description because it's much more natural to work with this, and especially when you are writing cosets and so on, it's useful to have this notation. So now let's work out the cosets of a particular subgroup and verify counting formula and the Lagrange's theorem in this case. So this is my ambient group G. Consider a subgroup I can take anything I want. So let me take the subgroup as an example given by H equal to E and 1 2. So remember, we have already verified that this is a subgroup because 1 2 times 1 2. Oh, so I should also tell you how to multiply these things. So you start with the right hand side. So 1 2 times 1 2 and you trace what happens. So for example, under the product, where does 1 go? 1 goes to 2 under the first element, then 2 goes to 1 under this. So 1 goes to 1. So there is no need to write it. If a number is not there, it is basically by itself within the bracket. 2 goes to 1 under the first function and 1 goes to 2. So 2 goes to 2 under the product. Similarly, 3 goes to 3. So this is E. Okay. So just as a practice, for example, we will do this as part of writing cosets. But what would be 2 3 times 1 2? 2 3 times 1 2. As I said, you start on the right hand side. You start on the right hand side element and work from there. Under the product, where does 1 go? You do first, where does 1 go? You ask yourself, where does 1 go under the first function, first element? 1 goes to 2 under the first element, but 2 goes to 3 under the second element. So in the product, 1 goes to 3. So you have 1 3 in the product. Now where does 3 go? 3 goes to 3 under the first element because 3 is not appearing in the first element. So 3 goes to 3 and 3 goes to 2 in the second element. So in the product, 3 goes to 2. Okay, let me see if I can close the bracket. Where does 2 go under the product? In the first entry, on the rightmost entry element, 2 goes to 1, right? And where does 1 go under the left entry element? 1 goes to itself. So 2 goes to 1 in the product. So the product of 2 3 1 2 is 1 3 2. So H is a subgroup. Now let's come back and calculate the left cosets of H in S3. So this is the problem. Compute the left cosets of H in S3. What are the left cosets? Remember, left cosets are elements of G multiplied by H. Element is on the left hand side. So this is EH, 1 2H, 1 3H. Elements are now defined like this: 2 3H, 1 2 3H, 1 3 2H. So these are the left cosets. But remember, you will expect that some of them may coincide with each other. So that's what we have to figure out. So what is, let's compute what is 1 2H. So 1 2H, remember, recall in general what is the left coset AH. In the general case, it is the set consisting of A times small h. In our example, 1 2H is, and H was E and 1 2. I'll fix that here. So H is E comma 1 2. So 1 2H is 1 2 times E and 1 2 times 1 2. I'm going to multiply each element of H by 1 2. So 1 2 times E and 1 2 times 1 2. And what is 1 2 times E? E is the identity element. So that's 1 2. And 1 2 times 1 2, as I worked out in the previous slide, is just E. 1 2 has order 2. So 1 2H is just 1 2 comma E, which is exactly equal to H. So the first two cosets here coincide. So EH is same as 1 2H. Now let's compute 1 3H. What is 1 3H? 1 3 times E and 1 3 times 1 2. 1 3 times E is 1 3 because E is the identity. What is 1 3 times E 1 2? I am going to use the same procedure that I described earlier, and you have to do this repeatedly if you are new to this to get used to the product of this cycle notation. You have to ask yourself, put a bracket, put 1. You can start with any number, right? So let's start with 1 and let's determine the image of 1 under the product. So it's a composition of functions. That's all this is happening here. 1 goes to 2 under the first function, 2 goes to 2 under the second function. So 1 goes to 2 under the composition of the two functions. Where does 2 go? 2 goes to 1 under the first function and 1 goes to 3 under the second function. So 2 goes to 3 under the composition. So I put 3 there. 3 goes to 3 under the first function because 3 is not appearing in this cycle notation, and 3 goes to 1 under the second function. So you close. So 1 3 1 2 is 1 2 3. So this is a coset. So this is what 1 3 H is. Now let's compute 1 2 3 H. 1 2 3 H is 1 2 3 E times E and 1 2 3 times 1 2. Before I compute this, let me just write 1 2 3 E is 1 2 3. Before I compute this product 1 2 3 times 1 2, let's look at the previous coset 1 3 and 1 2 3, and this coset is 1 2 3. So the coset 1 3 times H and the coset 1 2 3 times H have something in common. 1 2 3 is common to both of them. And remember our general theorem about equivalence classes of an equivalence relation, which applies to left cosets of a subgroup in a group. If two cosets have anything in common, they must be identical. This coset has, these two cosets have 1 2 3 in common. So you expect from that result that these are identical. So you expect in this place 1 3, it must be 1 3. If it's anything else, then these two cosets have something in common, yet they are not equal. It has to be 1 3, but let's verify just for surety that it must be 1 3. So in other words, what is 1 2 3 times 1 2? Following the same recipe for the product, I put 1 here. 1 goes to 2 under the first function, 2 goes to 3 under the second function. So 1 goes to 3 under the product. 3 goes to 3 here and 3 goes to 1 here. So 3 goes to 1 under the product. So you finish the bracket. Now what happens to 2? 2 goes to 1 here, 1 goes to 2. So 2 is fixed and no need to write that there. And sure enough, this is 1 3. So these two cosets are same. So this is same. Similarly, we have to compute, let's say 2 3 times H. What are these? What is this? This is 2 3 times E and 2 3 times 1 2, because H is 1 2. And 2 3 times E is 2 3, and 2 3 times 1 2, I will let you calculate using the same procedure. It will give you 1 3 2. Okay. Now the only remaining coset we have to compute is, remember there are 6 potential cosets: EH, 1 2H, 1 3H, 2 3H, 1 2 3H, 1 3 2. We have identified the first two. So I will write this later. We have identified the first two, and 1 3 happen to equal 1 2 3. This and this. Now let's do 2 3 and 1 3 2. What is 1 3 2 H? This is 1 3 2 times E and 1 3 3 2 times 1 2. Again remember, H is E and 1 2. So 1 3 2 times E is 1 3 2, and exactly as before, because they have something in common, they must be identical, which you can also verify by explicitly multiplying this out. And I strongly urge you to do this on your own. 1 3 2 times 1 3 2 times 1 2 is actually 2 3. So these two cosets are equal. So there are, let's now list all the distinct cosets of list all the left cosets. Again I am working with the specific example. H is E and 1 2. Okay, so this is EH and 1 2H. This is one coset. This is the first. Okay, this is the first left coset I wrote. The second one is 1 3H, which also happens to be same as 1 2 3H. This is the second left coset. And finally we have 2 3H, and that's equal to 132H. This is the third left coset. Remember that S3 has 6 elements. So potentially there are 6 left cosets, right? Because for each element you multiply by H. So EH, 12H, 13H, 23H, 123H, 132H. So there are 6 potential things, but because of identifications, because they are not all distinct, there are only 3 left cosets. There are 3 left cosets of H in G. In other words, the index of H in G is 3. In my notation that I developed earlier, G colon H is 3. That means G was S3. So let me write S3 colon that this particular subgroup is 3. So is the counting formula verified in this case? Recall what is the counting formula. It says order of the group equals the index of H in G times order of H. In our case, order was G was S3, so this is 6. Index we just calculated is 3. And what is order of the group? Order of the group is 2. There are 2 elements. So 3 times 6, 2 equals 6. So this is correct. Counting formula is verified, and Lagrange's theorem is also verified here, of course. For that you don't need to do any coset calculations, right? Because order of H, which is 2, divides order of S3, which is 6. So as an exercise, I will strongly urge you to do this to get comfortable with calculations of cosets. Compute the left cosets of H. New subgroup I take is H is E 1, 2, 3 and 1, 2, 1, 3, 2. So first of all, verify that this is a subgroup and compute its cosets in S3. Counting formula tells you how many you expect. Counting formula says how many cosets should be there. What is order of H? Order of H is 1, 2, 3. 3 elements are in H, so order of H is 3. Order of S3 is 6. The counting formula says 6 equals index of H in G times cardinality of H. In this case, cardinality of order of H is 2, 3. So the number of cosets should be 2. So verify this by explicitly computing the left cosets. See that there are 2 left cosets of H in G. So this tells you that there are 2 left cosets of H, this particular H in S3. So before, so this is an exercise for you. I will let you do this. I am not going to discuss this. Exactly the same calculation. But in this example, I also want to illustrate the fact that left cosets partition your group. So, and that is clear, right? Because S3, remember, is E12, 13, 23, 123, 132. And left cosets cover all the 6 elements. So left cosets are, in the previous slide, in the next slide we computed this, EH and 12H are same. So that and what is EH? EH was E and 1, 2. So 2 elements are in the first left coset. There are 2 more elements, 1, 3 and 1, 2, 3 are in the second left coset. 2, 3 and 1, 3, 2 are in the third left cosets. So we also see, so maybe I'll just record this here. In this example that we worked out, we also see that each left coset, this example is not the exercise, the example of, in the example H was E and 1, 2. each left coset has 2 elements. Remember, this is what you would expect because of a theorem that I proved earlier. Because H has 2 elements, each left coset of H has 2 elements. I want to say each left coset of H has 2 elements, which is what we noticed in the calculation. Every left coset, see 1 2 H is 1 2 and E, 1 3 H is 1 3 and 1 2 3. There are 2 elements. And there are 3 left cosets. Each coset has 2 elements. There are 6 by 2 equal to 3 left cosets. Again, this is counting formula, right? Number of cosets is the number of elements in the group divided by number of elements of the subgroup. There are 3 left cosets, and left cosets partition. This also we saw. So all 3 properties that we proved in general, we have illustrated them in this example, and I want you to do the exercise with a different subgroup of S3, namely a subgroup of 3 elements. Here what do you expect? Each left coset should have 3 elements. There should be 2 left cosets, and again all the left cosets should partition the group. So do the exercise, compute everything, all the left cosets, and verify that all the properties are satisfied. So in this video we have done a very important theorem called Lagrange's theorem, which says that a group, if you have a finite group G and a subgroup H of G, the order of H divides order of G. This is an extremely important theorem, and we proved that as a consequence of counting formula, which is also important, which says that order of a finite group is the product of order of the subgroup H and the index of H in G. And we have illustrated all these results in the case of S3, and in order to do that we have found a new description of elements of S3 using cycle notation, which is very important and that we will use repeatedly in future, and worked out all the left cosets of a particular subgroup H of S3. Thank you.